All right, let's jump right into it. If you're anywhere near computer science, you've definitely run into recurrence relations. They pop up everywhere, right? From sorting algorithms to complex data structures, but let's be honest, solving them can feel like a total drag. Today, we're going to change that. We're going to crack the code with an awesome tool called the Master Theorem.
So, does seeing something like this make your brain hurt a little? Yeah, I get it. You've got functions calling themselves, ends all over the place. It looks messy. But what if I told you there was a hidden pattern, a shortcut that could get you the answer like instantly?
Well, that's exactly what this is. The Master Theorem is basically a cheat code for algorithm analysis. It's a rock-solid formula that lets you look at most of the common recurrence relations, slot them into one of three simple categories, and bam, you've got your answer. No more drawing out endless recursion trees or just guessing.
So here's our game plan for today. We're going to start with the shortcut itself, a super simple three-step process. Then we'll break down the three possible results. We've got case 1, case 2, and case 3. And we'll go through tons of examples for each one. And of course, we'll wrap it all up with a quick recap to make sure it all sticks. You ready? Let's do this. Okay, first things first, we need a framework. Before we can even think about using this cheat code, we've got to make sure our problem is set up in the right way. So let's take a look at what that format is. The Master Theorem only plays ball if your equation looks like this. This is the standard form. Think of it like this. A is how many new smaller problems you're creating at each step. B is how much you're shrinking the problem each time. And f of n? That's all the extra work you have to do, like combining all those little answers back together. And here it is, your three-step master plan. It's actually that simple. Step 1, just pull the a, b, and f of n values right out of the equation. Step 2, you calculate this one critical piece of information, n to the power of log base b of a. And finally, step 3, you just compare what you got in step 2 with your f of n. That's literally it. This one comparison tells you everything. And this table right here shows you exactly what that comparison means. It's like a showdown between two functions. If your calculated value is polynomially larger than fn, meaning it grows way faster, you're in case 1. If they're pretty much growing at the same rate, you've got a tie, and that's case 2. And if fn is the one that's growing faster, well, that's case 3. This simple comparison is the key that unlocks the whole puzzle. All right, let's dive into our first scenario. Case 1. This is what happens when the work of breaking the problem down, the recursion itself, is the heaviest part of the whole process. It totally overshadows the work you do to put the pieces back together. Let's use this as our first example. T of n equals 4 times t of n divided by 2 plus n. Let's put it through our three-step plan and see what happens. Let's do it. Step 1, identify the variables. Looking at our formula, a is 4, b is 2, and our f of n is just n. Easy enough. Now for step 2, we calculate n to the power of log base 2 of 4. Well, log base 2 of 4 is just 2, right? So our result is simply n squared. And now for the big showdown, step 3. We're comparing n squared against n. As you can see, it's not even a fair fight. N squared grows times way faster than n. This lopsided result tells us we are definitely 100% in case 1. So, what's the final answer? The rule for case 1 is that the time complexity is simply theta of that term we calculated, the powerful one. In our example, that means the solution is just theta of n squared. And we're done, see? No recursion tree needed. Let's do a quick rapid-fire round to really nail this down. For 2tn over 2 plus 1, log base 2 of 2 is 1, n to the 1 is obviously bigger than a constant 1, so the answer is theta of n. Next, 8tn over 2 plus n squared, log base 2 of 8 is 3, n cubed beats n squared, so the answer is theta of n cubed. Last one, 16tn over 2 plus n squared, log base 2 of 16 is 4, n to the 4th power crushes n squared, giving us theta of n to the 4th. See the pattern? It's always the same. Okay, moving on to case 2. I like to call this the balanced case. This is what happens when the cost of splitting the problem up and the cost of putting it back together are pretty much the same. They're perfectly matched, running neck and neck. A perfect example of this is the classic merge sort algorithm, which gives us t of n equals 2t of n by 2 plus n. Here, a is 2, b is 2. So we calculate n to the power of log base 2 of 2, which is just n. And guess what? Our f of n is also n. It's a dead heat. The two sides are perfectly balanced. Now, when you get a tie like this, there's a special rule. The final complexity is theta of f of n, but you have to multiply it by a log n factor. Why? Because the work is spread out so evenly across all the levels of recursion, and the number of levels is related to log n. So for merge sort, the answer is the famous theta of n log n. This is a super important one. Case 2 has a few tricky variations, but they're easy once you see the pattern. What if your f of n already has a log in it? Simple. You just bump up the power of the log by 1. So if f of n was n log n, the final answer becomes n log squared n. And what if f of n is being divided by a log? Then the answer becomes n times log of log n. And that brings us to our final case, case 3. This is the complete opposite of case 1. In this situation, all that work you do outside the recursion, that f of n part, is the real heavyweight. It's the bottleneck of the whole operation, growing much faster than the recursion cost. Let's check out t of n equals 2t of n over 2 plus n squared. We already know our calculated term is n. This time, our f of n is n squared. You can see it right away. The f of n side is way heavier. The comparison is a no-brainer. Our recursion term is polynomially smaller than f of n. And you know what? The rule for case 3 is the easiest one of all. The answer is simply theta of f of n. That's it. Whatever that dominant function is, that's your complexity. So for our example here, the solution is just theta of n squared. Done. And here's a super important note. Unlike case 2, you don't add any extra log factors here, ever. If your f of n is, say, n squared log n, and it wins the showdown for case 3, then your answer is exactly that, theta of n squared log n. You just take f of n as is. Phew, we've covered a lot of ground, so let's take a second and boil all of this down into one simple, powerful cheat sheet. This is the one you'll want to screenshot or jot down. And here it is, the whole thing in a nutshell. Just remember it like this. Case 1, the recursion part wins. Your answer is that calculated term. Case 2, it's a tie. Your answer is f of n with an extra log factor tacked on. Case 3, the function part wins. Your answer is just f of n. All you have to do is follow your 3-step plan, see which of these 3 scenarios you're in, and this table gives you the solution. So there you have it. You now have the master plan. You can look at a huge number of these intimidating recurrence relations and solve them in just a few seconds. Now the ball's in your court. Think about the famous algorithms you already know: merge sort, binary search, maybe even some more complicated ones. Which case does each one fall into? Give it a shot. Thanks for watching.